So this is problem 90 from chapter 2. 90. So we have a police car at rest that's passed by a speeder traveling at a constant 130 kilometers per hour and takes off in hot pursuit. The police officer catches up to the speeder in 750 meters, maintaining a constant acceleration. And for part A, they're asking us to qualitatively plot the position versus time graph for both cars from the police car's start to the catch-up point. Before I do that, I'm going to draw some diagram, set up my coordinate system and things like that. So this is a one-dimensional problem. I'm going to choose some direction and some origin. So the origin is going to be where my police car is waiting, let's say, right? And the other car just passes this point at the origin at 130 kilometers per hour, and then they go at 750. They catch up. The police car catches up to the car. Now the first thing you should do is to convert this to meters per second, because we are using MPS units. We're going to find our answer in seconds and things like that, and our length in meters. So you should convert this. This is very easy. So this is going to be 130,000 meters per hour. Now 130,000 divided by 3,600 meters per second. And so you just multiply it by 1,000, divide by 3,600, you get it in meters per second. All right, so part A is what does the position versus time graph looks like. So let's use different colored chalks here. For the car, it's starting at t equals 0, let's say at the origin where I did this, and they're going to be moving at constant velocity. So for the car, which I'll use a red chalk, it's going to be a straight line. And the slope of that line is going to give 130 kilometers per hour converted to MKS units. For the police car, they are going to start at 0 velocity and they're going to have a constant acceleration. A constant acceleration motion looks like a parabola in x versus t graph. And they're going to start with 0 slope because they start at 0 velocity. And this is what the parabola is going to look like. And they're going to have 750. This is 750. Okay? And the slope is 130 converted. Okay? Let's say converted here. Okay. You can put the slope, you don't have to put the slope. They're saying, qualitative, not quantitative. So it doesn't have to be too accurate, but if you can put some information on the graph, it's of course helpful. I don't know if this can be read easily. This is a parabola with 0 slope here, so it will be symmetric around the vertical axis. How long it took police officer to overtake the speeder? So they're asking for this one. Delta T for part B. Let's do part B here. Now, how would we do this? Well, they both spend the same time, but there's actually a shortcut here. There's a shortcut. So one of the objects is doing constant velocity motion, and we know how much distance it covered. So I can just use constant velocity and find delta t from there. So for constant velocity, delta x is going to be just v times delta t. Okay. This is 130. You have to convert it. It's not 130. This is 750. And you can find this by a simple division. Okay. So it's a shortcut. We don't need to complicate things. This is how we can get the answer to part B. The required police car acceleration. Now, before going to this, you could go wrong. You could go wrong. So this is something that you need to do. This is correct. But you could, for example, say that at the meeting point, their velocities are the same. So the police is reaching 130 kilometers per hour. And so I'm going to use something like this. V0 plus a delta t, something like that. You can't. Okay? And in fact, you could try to use this for the second one, the required acceleration of the police car. Okay? So the part C is the required police car acceleration for this. You can't use that. Okay? what's the acceleration of the police car? You can't do it, you can't find it this way. So you can't say v naught plus a delta t, and I calculated delta t here, I put it here. My velocity at the point of catch-up is 130 kilometers per hour. It is not. It is not. If you look at this graph, the slope of this parabola is going to be higher than the slope of this straight line. Okay? And the slope gives the velocity. Velocities are not the same. The velocities are going to be the same somewhere over here. Okay? Way before it catches up. At this point, there's still a difference between their positions. There's some delta x between the police and the speeder. And so you should not use this. But what can you use? What can you use to find the acceleration? Well, there are a couple things you can do. But one of the things that come to my mind, if I write the position for the police car, 0 plus v0 delta t plus 1/2 a delta t squared. Okay. Now, this one I know. Okay, they catch up at 750 over here. So this is 750. This is 0 by my choice. I start at rest. I start at rest, so v0 is also 0. And then I can find for acceleration because I solved for delta t in part B. And this is how I would go about this. Okay? There's a little pitfall, and I think that what makes this problem interesting is that pitfall. Hopefully you've seen it, and you're not going to fall into it. The speed of the police car at the overtaking point. Now we can actually use the formula that we should not have used for the previous part. So for part D, V is V0 plus A delta T. Now this is delta T we calculated here. Okay? And then our start at 0. Delta T comes from here. Acceleration comes from here. And we can find our V by plugging numbers in that we found in the previous parts. And this is constant acceleration motion. So this holds. You start at rest. You move with some acceleration that you find in previous part. You spend some time over here, and you're going to get this. Now, if you solve for this, you're going to find that this is something simple. I think it comes to something like twice V0 or something. But again, there is no point in memorizing this. And the point of the problem is not really, getting the answer. It is applying certain formulas, and more importantly, it is knowing when to apply what formula, and that requires an understanding of the situation and so on and so forth. Like, look at the situation, and you make it similar to another one and use a shortcut formula. That's not the point of this problem. Okay? You're not understanding physics that way. Physics doesn't work that way. Nothing works that way. You have to understand what's going on, describe the problem, and you should use general tools to attack the problem so that you can actually use those tools to attack other problems. If you use specific tools for this one, then you can't solve other problems. And the point of these problems is really having a general understanding. End of rant.